So, hi Evan. There's been a request to go over 2014 number 4, part C. And so I'm going to take this opportunity to actually review numerical integration in general, right? So, what we have for an integral of f of x dx is that we can estimate it using a table of values with a left sum, a right sum, a midpoint sum, or a trapezoidal sum. And there are two things that you definitely, that's a string abbreviated midpoint. Let's try that again. There we go. So there are two things that you definitely need to know, AP-wise, for each of these sums. And then there's one additional thing that you should probably know for just for the sake of cultural enrichment. And the two things you definitely should know are how to construct each one and qualitatively what we can say about the error for each one of these. First of all, how to construct. Let's take our table of values that are given to us from the problem and talk about how we would construct a left sum, right sum, midpoint sum, or trapezoidal sum for each one. Now I know that's overkill because we were only supposed to do trapezoidal for this problem, but I want to generalize it so you can see how each works. Because every year, questions asked, here's some data, now estimate the integral with one of these sums. And so you have to be able to demonstrate your competence with all of those. TVA 025812. Here, we're going to give ourselves a table with 6. Yes? Yeah. I was talking to my board. 025812, and now we go back to VA 0, 140, minus 120, minus 150. Okay, and one more thing, crucial to this, the units, minutes and meters per minute. Like so. Yep. But we're going to focus just on the integral part right now, and then we'll focus on what it means, and that's where the starting position will become relevant. So, if I want to estimate the integral from 0 to 12 of VA dt using a left sum, right sum, or midpoint sum, I need to first of all partition. And for the left sum and the right sum and the trapezoidal sum, my partition is going to be according to the number of intervals that they tell me. Counting data points here, 5 data points, out of that I can form a partition with 4 different subintervals, right? Or I could form a partition with any number less than 4 subintervals also, simply by grouping these cells together if I wanted to. But usually, they will have you partition it into as many subintervals as possible. And so that would be 4 in this case. And for each subinterval, I'm going to go through and I'm going to mark the delta t for that subinterval. So here we have 2, 3, 3, and 4 minutes for each subinterval. This works well for the left sum, for the right sum, and the trapezoidal sum. It's not going to work for the midpoint sum. That's going to be special, and I'm going to have to come back to that in just a minute. Now, if I want a left sum, then for each subinterval, I'm going to come and choose the value on the left. And so that's going to give me 0 times the delta t here. Keep in mind that your sum is the sum of VA times delta t, which is the discrete approximation of the integral dA dt, right there. So notice the correspondence between our symbols here. Okay. So I have 0 times 2 plus 100 times 3 plus 40 times 3 minus 120 times 4. And units, meters per minute times minutes for each term. And so I would express that as meters, which is meters per minute times seconds. That's my left sum. Right sum, very, very similar, but I'm going to pick the values on the right-hand side. And that's going to give me 100 times 2 plus 40 times 3 minus 120 times 3 minus 150 times 4. Again, meters. Yes?
You can pretty much just draw like arrows connecting to like left sum.
Yes, that's right.
Slanted arrow down, right sum is a slanted arrow to the right.
Yeah. I usually just go through and like mark with arrows like this. That's my left sum. Here's my right sum. For the trapezoidal sum, I need to do just a little more work because you remember that the area under a trapezoid is going to be average height times the width. And so for my trapezoidal sum, I'm actually going to have to come through and do the averaging. And I just killed all my values. 0, 40, 100. So I'm going to go through for my trapezoidal sum. Let's do that in black. And average each one of my VAs across the subinterval. So the average here is 20. The average here is going to be 70. The average here is going to be negative 10. And the average here is going to be negative 135. And so we have average height times width is 20 times 2 plus 70 times 2 minus 10, 70 times 3, right? Minus 10 times 3 and minus 135 times 4. And again, meters. And that's my trapezoidal sum. For all three of those, the common student mistake is to multiply height times t instead of delta t. Right? So I get a lot of papers where I've got 0 times 0 plus 40 times 2 plus 100 times 5. No. We're looking at height times width, which is delta t. Lydia, did that answer your question about trapezoidal so far? Before we do okay, good. The midpoint sum is a little different because for the midpoint sum, I'm going to choose values at the midpoint of each subinterval. And since I do not know the values of v at the midpoints of each of these 4 subintervals, I cannot do a midpoint sum with 4 subintervals here. The best that I can hope for with a midpoint sum is a midpoint sum with 2 subintervals, where I include data points across the middle. But if I do that, I have to be lucky and know the values at 2.5 and again here at 8.5, and I don't. So a midpoint sum is not possible unless you happen to know the values at the midpoint of each subinterval. And if I have 5 data points, the most I can hope for is 2 subintervals out of those 5 data points, because I need 3 data points for each subinterval for a midpoint sum. And the middle one has to be exactly at the midpoint. Does that make sense? So midpoint sum is not even possible with this data set. If this were 2.5 and 8.5, then I could do a midpoint sum by doing 5 times 40 and 7 times negative 120. Yeah.
When do we use like Riemann instead of Riemann?
So these are, well, the trapezoidal is not, but the Riemann sum, the trapezoidal is the average of 2 Riemann sums. It's close, it's cousin. These are all Riemann sums. because they are in the form sum of VA times delta T, where the delta T's are formed by partitioning my full interval. So they are legit Riemann sums. If my delta T's all happen to be equal, if I have a partition of equal width, then each width has to be the whole length divided by the number of partitions, the number of subintervals. So then my delta T would be V minus A over N. But if it's not, it's not. And there it is. So one thing that students will do is they will memorize the formula for the trapezoidal sum, B minus A over 2n times f of plus 2, which only applies if I happen to have equal weights of intervals. So how does that work out? For the mathematician, it works out great because you can take a function, a continuous function, and arrange it so that you're dividing it up into equal weights of intervals. For a scientist, it's terrible because when you do your sampling, unless you're extraordinarily lucky, your data will not come out in equally spaced subintervals to the nearest whatever place, right? So you're going to need to do it as I've done it here. Now I promised that you needed to know something about error, so let's talk about that for just a minute. For the left sum and the right sum, the error is found in the first derivative. And to see that and remember it, you want to take an example for yourself. And the typical example that I usually do is a curve like this. And I want to know what is the error when I do a left sum or a right sum or a trapezoidal sum approximation. For the midpoint sum, I'm not going to be able to say anything about the error. Things can be said, but they're too complicated to say. But for the left sum and the right sum and the trapezoidal sum, I can use a single subinterval here, the entire thing, to help me remember what's going on. Notice that this curve is increasing and it is concave up. What happens if I estimate the area with a single interval left, a single subinterval left sum? Let me make that green so I have to use my color sleeve down here. So this is my left sum right there. Is it an overestimate or an underestimate? It's obviously under. Why does it have to be under? Because an increasing function will always have my left sum be the minimum value, which means that the left sum is the lower sum, which is always guaranteed to be the smallest possible Riemann sum. If f prime is positive, then the left sum is an underestimate. Now, on the other hand, if I do a one rectangle right-hand sum in blue, it is guaranteed to be an overestimate because an increasing function will always have its largest value on the right-hand side, which means that the right sum is the upper sum, which is guaranteed to be the largest possible Riemann sum. So if f prime is greater than 0, then we have an overestimate. What about the trapezoidal sum? Let me do that in black. My trapezoidal sum with one subinterval right here is clearly an overestimate. Why? Because my curve, being concave up, goes below the secant line, not the tangent line. The curve is above its tangent lines, but it dips below that secant line because its f double prime is going to be greater than 0 compared to the line where f double prime or y double prime is equal to 0. And because of that, that means my curve is going to start off with a lower rate of change than the line, and it's going to have an increasing rate of change, concave up, and end up with a rate of change that is greater than that of the line. And for that reason, it is going to lie, the curve lies below the secant line. So this guy right here, f double prime is greater than 0, and then we have the trapezoidal sum is an overestimate. So notice that the left and the right sum look at the sign of f prime to determine whether we're over or underestimating. The trapezoidal sum takes a look at f double prime. And that is also reflected in the error-bound formula for the trapezoidal rule. So this is the piece of cultural literacy that is not tested on the exam but is worth knowing. And that is that the error in the trapezoidal rule is bounded by, you can write it as b minus a cubed over 12n squared times the max of f double prime on the interval a to b. There's a couple of different ways to derive this formula. One of them uses actually Taylor series to do it. We're not interested so much in as why it works as kind of the mechanics of how it works. Here are the things that I want you to observe about it. And the first is kind of obvious. The larger the number of sub-intervals that I use, then the smaller the error will be. That's kind of obvious. And the second is, the smaller that f double prime is in magnitude, then the smaller my error will be also. In other words, what does a curve look like if it has a small f double prime? Yes, that would be the extreme case, right? So the minimum possible we could get would be 0, and if f double prime is identically 0, that means that f prime is constant, which means that I have a line. So the first fallout from this is that the trapezoidal sum gives you perfect area for a straight line. Well, I guess it makes sense, doesn't it? Because then your trapezoids hit the line. Okay. And backing off of that, if I have a small but non-zero f double prime, what does that mean about the shape of my curve? If my f double prime is not 0 identically, but it's small, what does that mean about the shape of my curve? It's going to be flattish. That's right. It's going to be very gentle. Whereas if f double prime is really large, what's my curve going to look like? It's going to be wiggly. That's exactly right. So wiggly curves are going to tend to have larger errors in the trapezoidal sum, and flat, smooth curves are going to have very good trapezoidal sums. Okay? That's enough said about that. Coming back to our problem, that is a long-winded way to get at this. At time t equals 2, train A's position is 300 meters east of the origin station. That's original. And the train is moving to the east. Write an expression involving... Oh, you meant for D. So you were all good with C. Well, do you want me to do C anyway?
Yeah. We already did all the work.
Let's do C. That's right. Okay, 300 meters east of the origin station, train is moving to the east. Write an expression involving an interval that gives the position of train A in meters at time t equals 12. Okay, if I integrate the velocity, I'm going to get the position. No, the change in the position. So I need to represent the position. Do I have a variable for that? No, they don't give me a label. Bad problem. All right, then we're going to call it A for train A. And train A's position is going to be equal to then the original value, the initial value, 300 meters east and moving east, plus the integral from 0 to 12 of the velocity dt. Notice that it's not possible to give a formula for the velocity, so I just use it for the. And then we approximate it with the trapezoidal sum. 3 subintervals indicated by the table.
Starting at 2.
Ah! Hey, how about that reading the problem thing? It catches everybody, doesn't it? The 3 subintervals made me stop and reflect. What did I do wrong? And the answer was, didn't read the problem. Good. Nice to have a Charlie over your shoulder, too, to help you out with that. So there it is. So we go through and we mark our 3 subintervals with their deltas, like so, and their average. Heights, like so, and our full answer on the answer sheet would look like this. We would say that A is equal to 300. I don't know whether it is oversight or intent. Did I do something wrong?
No,
Zipper down? Whether it is oversight or intent that they did not give us a label for, for the position here. Some problems they do, and this problem they do not. I don't know if that means that they want, that a particular skill they want to test is whether or not you can create a label for your own things. Let's see here. So the units are meters per minute times minutes. So meters. Oh, the label for your position. They didn't give us a label. Yeah, not the units, the label.
I think they didn't give us a label because I'm pretty sure on the scoring, you got 1 point for the integral, and then you had to call the trapezoidal sum alone something else, and then that you said A equals 300 plus the trapezoidal sum.
This would get full credit for sure. It's very clear. You've got your initial value plus your trapezoidal sum. So I think in doing that, they're not trying to force you to write it in separate lines. They're simply saying you get separate points for the following things. So you get 1 point here for this quantity, you get 1 point for that quantity, and 1 point for adding 300 to it. Finally, at long last, we get to Sam's question, which is B. A second train B, travels north from the origin station. At time t, the velocity of the train B is given by blah, blah, blah. And at time t equals 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. Lovely. So they took this and they added their related rate problem. It has become the thing to kind of sneak a related rate problem into one part of one problem. And so here it is. Thought process. I want to find the rate at which the distance is changing. To back that up one level, I need to find the distance as a function of time t, and then find that rate as a derivative. Does that make sense? So let me do that quantitatively here. I've got 300. I'm just going to write that. I'll write this 300. And I've got 400. Let me do this really simply rather than make it complicated. If I do it simply, then train A is going to be here at some time t, train B is going to be here at some time t, and what basic geometric thing is going to give me the distance between them? Okay, be specific. What kind of triangle leading to what kind of equation? Which is who's there? Yes. All right. So, really then, we can say that distance squared is equal to a squared plus b squared. Also, as a bit of cultural literacy, it is a little bit easier to optimize distance squared than or to find the rate using distance squared than it is to find the rate using distance. Slightly. Okay. Now, how can I represent A? Well, I've already represented A. A is 300 plus the integral from 2 to t of velocity. It's looking a little yucky, but I'm not scared. And likewise, there we go. This guy is a representation for my distance b. Notice that this is sort of high-level thought, right? Because I haven't gone through and plugged in anything at this time, and I'm not going to. Okay. Let me make sure that I've read the problem correctly, because the 400 should correspond to t equals 2. Yes. I just want to make sure they didn't do anything fancy. Okay. Now, we also know these distances right here at 300 and, at t equals 2, we're actually at this point right here and at this point right here. So coming back and looking at the problem a second time, we want to refine this. And as soon as we do this, of course, we know the distance here. What is that distance? 500, right, because we recognize the 3, 4, 5 right triangle. Okay. So I've got a distance of 500. So this is my d squared. Now that I have that, I'm ready for a derivative. It's all constructed. It's a little weird, but I'm ready for a derivative. So when I take the derivative, bless you. And I run out of space. There it is. Then on this side, I get 2 times the distance times the rate at which the distance is changing. That's magic. That's what I'm looking for. And on this side, I'm going to have to go through term at a time and be careful. I'm going to get 2 times 300 plus the integral from 2 to t of va dt. And here it comes, times the derivative of the inside, which gives me fundamental theorem, which gives me va. The derivative of 300 being 0, and the derivative with respect to t of the integral from 2 to t being va. And here, same thing, 2 times 400 plus the integral times dv. Now, this was ugly. They make up for it on the back end by having everything be lovely. Because d I already know is 500. And t is 2, so this integral actually disappears in the computation. This integral likewise disappears in the computation. And now I just need to look up the values of VA and VB at t equals 2. And the value of VA comes off the table, which is 100. Along the way, I cancel out 2's. And the value of VB, it better be measured. According to the problem, it's this kind of yucky thing. I'm going to have to actually evaluate it. I don't have a calculator, so I'm hoping it's nice. That's going to be minus 20. It's going to be minus 20 plus 120 plus 25. And so to me, that looks like 125. And because I'm in not a particularly happy frame of mind with them for giving me such a technical problem, I'm going to leave it for them to figure out my answers right now. But I don't want to forget units. What kind of units do I get out of this? I've got meters per minute for this guy. I've got meters for this guy because it's a distance, divided by meters here for distance, and I get meters per minute, which is exactly as it should be.
Why did you go with the integral? Why couldn't you just scroll up for a second? Why didn't you just take the derivative of b squared equals a squared plus b squared? You get 2d d prime
Yes.
plus 2a prime, and just do it.
That's a great point. So it may be that by substituting here, I made my life not a little more complicated maybe than it needed to be. because once I have got a relationship right here, I can take a derivative at any time, as long as I'm doing it before I substitute values, right? So what I could have done is to take a derivative at this point. I really like your suggestion, John. I think that's wise.
Since it's at the same time, then you can just plug in the position.
And then you can plug in the position, the known positions, and you can kind of skip some of your fundamental theorem. But, well, you can't really skip the fundamental theorem, though, because you need to recognize that this is velocity at some point, right? So you're going to have to still recognize that this is a value, and this is VA, and this is VB. So I like that. That's clean. That's good.
The time was like at t equals 4, though, you'd have to do your
But you could still do it in pieces. So you could still say, hey, I need A at 4 and I need B at 4. And go find those pieces and substitute. So that's a legitimate way of doing it as well. So two different looks to our answer that are both the same thing, but they come about by reversing our order of operations. In the one case, differentiation first, and then substitution of algebraic values. In the other case, substitution and then differentiation. Good. Does that answer your question? Any other questions? Yes.
For this problem, part A is like an average. Does that mean F average or? I never remember.
Ah, okay. So, it's not so much a matter of remembering as it is a matter of translating. When I see that they're looking for average acceleration, and I look at the information that is given to me, I think to myself, acceleration is the rate of change of the velocity. And since I want the rate of change over the interval 2 to 8, then that means I need a slope.
2 to 8.
2 to 8, not 2 to 12. Yep. I am determined in this read today. So I can immediately write the average acceleration is equal to delta V over delta T. And that's going to give me minus 120 minus 100 meters per minute. Don't forget those units. Over 8 minus 2 minutes. And just leave it like that. Here's a second way to think about it. They're asking for an average acceleration. And I know that acceleration is dv dt. And what an average is doing it is simply evaluating this over a finite time interval. So that my finite estimate of dv dt is going to be approximately delta v over delta t, and that brings you back to this right here. Now let's contrast that with, find the average velocity of train A over the interval, blah, blah, blah. Finding the average velocity, v average, would be a matter of averaging all of these values because they are velocities. Not these values, because they are velocities. And so that would be a matter of adding them up, which we do with an interval or an estimate for an interval, and then dividing them by the total width that we have there. So that would be represented as 1 over 8 minus 2, integral from 2 to 8 of velocity. Does that make sense? So it's really a matter of translation rather than brute force measurement.
And that interval would have to be a... Yes.
You'd have to estimate it with a real and sum because you don't know all the values in each one.
So it's the slope for average.
For average rate of change. A rate of change is a slope.
You just do slope like you're doing like the equation.
Yeah.
The instantaneous is what you do.
Yep.
The
Yep. That's exactly right. And here's how they are connected to one another. Average rate of change and average value are actually connected to one another in this way. If I compute the average acceleration as the average of the acceleration, the average value of the acceleration, excuse me, by adding up all of my accelerations and dividing by the width. Now use fundamental theorem, and what do you get? The integral of acceleration is going to give you the change in velocity. It's going to give you v of b minus v of a over v minus a, which is delta v over delta t. So the average rate of change, average slope, is literally the average value of the rate of change. So that's the second way to think about it. Does that help? Okay. Good. Other questions? What can I do with my calculator? Well, you guys are experts at this point. I just want to give you a couple of advanced pro tips here. You can use your calculator for four main things: to visualize, and along with that, to find points on a curve using the trace. To find intersection points. Second calc intersect. To find derivatives at a point with second calc dy dx. Or inderiv. Do you guys use inderiv much? Or is it all second calc? I don't use it very much either. I use it only when I want to graph the derivative of something, and I want y1 equal inderiv function from x, or to find integrals. Okay, here are the pro tips. First thing to be aware of, when you have to find multiple intersection points, if I have to find where two curves are intersecting, for example, don't forget that you have to do the whole second calc intersect process for each point. Some students, and I've done this before, just not thinking, will find second calc intersect from that first intersection point, and then they will trace along the curve to get to the second intersection point. If it doesn't say intersection at the bottom of your calculator, it's not an intersection point, even if the cursor looks like it's close. So it must say intersection in order for it to be an intersection point. And if it's not, then don't trust that value. Okay. Second thing, derivatives. Yep, derivatives can lie also. If your function is not differentiable at a point, the calculator will give you a value anyway, because all it's doing is a difference quotient. So you need to look ahead and see whether or not your function reasonably should have a derivative at that point. Just verify that it doesn't have a sharp corner or a vertical tangent or a cusp at that point before you go second calc derivative. So check for differentiability. And the last thing, count your parentheses. Count your parentheses. For a stupid reason that I do not know, TI lets you put in fewer right parentheses than left parentheses, which means that you can sometimes deceive yourself as to what's being grouped if it's complicated, and that can lead to wrong answers. So just count your parentheses to make sure that you got the same number of left as right, because TI won't do it for you, unlike every other programming language in the entire world. Yes?
I know you can like put x values, but how do you make x equals something?
If you store a value into X,
Like, how do you do that?
you hit the STO button, which is here. So if I say to store, sorry. let's say 2, store in x, now x is 2. If you want to evaluate something at a given value of x, like for a Newton's method kind of a thing,